Welcome students for the chemistry lecture, and in the chemical kinetics you have studied what is the rate of reaction or velocity of reaction, then specific reaction rate, what is molecularity and order of reaction, distinguishing character points in between order and molecularity. Then you have studied first order reactions with characteristics and examples. Then you have studied the second order reactions and you have derived the integrated form of second order reaction where the initial concentrations are same one. And today you are going to learn the derivation of equation for velocity constant of second order reaction where initial concentrations of reactants are unequal or different. Okay, derivation of equation for velocity constant of second order reaction where initial concentrations of reactants are unequal or different. Okay, for this purpose, consider the second order reaction as A plus B, it gives products. Let the initial concentration of A, it is equal to small a, and the initial concentration of this B reactant, it is the small b, and decrease in concentration of each reactant after time t, it is equal to x. Okay, we have considered A and B are the initial concentrations and X is the decrease in concentration at time t. Then the concentration of A after time t, it is equal to A minus X, and the concentration of B after time t, it is equal to B minus X. Then the rate or velocity of reaction is then given by dx by dt. It is proportional to A minus x into B minus x, or dx by dt. This proportionality constant we have removed, and it is equated with k in a bracket A minus x into B minus x, where this k, it is the velocity constant or specific reaction rate or simply rate constant. Then therefore rearranging this equation dx by dt, it is equal to k into A minus x into B minus x. We get here dx upon A minus x into B minus x, it is equal to k into dt, and integrating this equation, that means integration of A minus x into B minus x, it is equal to integration of k into dt. We get 1 by A minus b into log to the base e A minus x upon B minus x, it is equal to k into t. Integration of dt, it is t, and k, it is the constant, therefore kt plus c, where c is the integration constant. And when t, it is equal to 0 and x, it is equal to 0, and putting t 0 and x 0 in this equation, we get 1 upon A minus b into log to the base e A by b, it is the value of c, and here substituting this value of c, we get 1 upon A minus b into log to the base e A minus x upon B minus x, it is equal to kt plus 1 upon A minus b into log to the base e A upon b. Okay, then see here, this right hand term we take towards left hand side, and our equation becomes 1 upon A minus b into log to the base e a minus x upon b minus x minus 1 upon a minus b into log to the base e of a by b. It is equal to k into dt. And in this equation we have a 1 upon a minus b common. So we have take this common and the equation becomes 1 upon a minus b into log a minus x upon b minus x minus this log to the base e a by b. It is equal to kt. Again, this is with negative sign, log of a by b. We change this negative sign as a plus sign and we have log to the base b by a. Therefore, we have 1 upon a minus b into log to the base e a minus x upon b minus x plus here log of b by a to the base e. It is equal to kt and the sum of two logs. Therefore, it becomes the log to the base e b into a minus x upon a into b minus x, and this 1 upon a minus b, it remains as it is. Therefore, our equation becomes 1 upon a minus b into log to the base e b in a bracket a minus x upon a in a bracket b minus x. It is equal to kt, and changing this log to the base e to the log to the base 10, here we have to multiply by this factor 2.303. Therefore, our equation becomes 2.303 upon a minus b into log to the base 10 b in a bracket a minus x upon a in a bracket b minus x. It is equal to kt. Therefore, we have k, it is equal to 2.303 upon t in a bracket a minus b into log to the base 10 of b in a bracket a minus x into a divided by a in a bracket b minus x. And this is the equation of velocity constant k of the second order reaction where initial concentrations are different. In this equation a, it is the initial concentration of a reactant, this b, it is the initial concentration of b reactant, and x, these x are the decrease in concentration, where this t, it is the time, and k, it is the velocity constant or rate constant. Then the characteristics of second order reaction. This the next point, that is the characteristics of second order reaction. The second order reaction can be recognized by their various characteristics or properties, and these are as follows. Here, the first characteristic, units for velocity constant k for second order reaction. Here, for second order reaction where initial concentrations are equal, we have the rate constant or velocity constant k, it is equal to 1 by t into x upon a in a bracket a minus x. Here there is one concentration term x in the numerator and two concentration terms a and a minus x are in the denominator. If these concentration terms are expressed in the same units, the velocity constant k will be inversely proportional to the concentration. The same conclusion can be drawn from the equation. Here there are one concentration term and here there are two concentration terms. Therefore, according to formula units, here concentration raised to 1 minus n into time inverse. The unit for second order k will be moles per liter raised to minus 1 into second inverse, that is liter into mole inverse into second inverse, or dm cube into mole inverse into second inverse in a SI unit. Then the time taken to complete any fraction of the reaction or half-life time is inversely proportional to the initial concentration. And here, for equal concentrations of reactants, we have K, it is equal to 1 by T into X upon A in a bracket A minus X. When X, that is the decrease in concentration, it is equal to half of the initial concentration, that is A by 2, and time T, it is equal to 1 half. In this equation, when we put the value of T as T 1 half and X as A by 2, we can simplify this equation. Okay, and we get T 1 half, it is 1 by A, that is the initial concentration, it is inversely proportional to the here time taken to complete any fraction of the reaction or half-life time of second order reaction is inversely proportional to the initial concentration. And the next characteristic, if one of the reactant is present in a large excess, then this reaction, it becomes kinetically of first order. Then the graphical representation we will see next time. Okay, thank you.